In this video, we're going to use 10 tricks in mathematical analysis to prove that e to the x plus y equals e to the x, e to the y. By the end of this video, you can use these exact same tricks and techniques to solve many problems in real analysis. But before we actually prove this equation, why bother with it at all? In some sense, this identity is what makes the exponential function really the exponential function. Firstly, it helps us prove many laws of indices that we take for granted in high school. Secondly, it helps us define all of the other exponential functions that we take for granted in high school. And we even get the same laws of indices applied to these other exponential functions. Finally, using the tools which we use to prove the exponential identity, we can show that the derivative of the exponential is itself. However, these properties all depend on the fact that e to the x plus y equals e to the x, e to the y. How can we be sure that this equation is actually true? Before any proof, we actually first need to define what e to the x means. There are many different definitions for e to the x, but we'll use the definition most accessible at the high school level. We can think of it as putting some money into a bank and then earning interest on our deposit. And we can ask, how much did our money multiply? If the bank offers you an interest rate of x and gives you one round of interest, your money gets multiplied by 1 plus x over 1. If, however, the bank gives you interest twice, the multiplier on your money will be 1 plus x over 2 times. If the bank credits you once every month, then the 2 becomes 12. If the bank credits you every single day, then the 12 becomes 365. And if the bank is so generous to credit interest to you at every single moment of your life, then the 365 will change into n, and n is going to get larger and larger and larger. This extreme situation is what we define to be e to the x. And while in the context of the bank, x is positive, as a mathematical construct, x can be any real number we wish. For those of you who know about complex numbers, we could define it this way as well. But for the purpose of the video today, we're gonna just stick to real numbers. With this definition of e to the x, we can now finally attempt to prove that e to the x plus y equals e to the x, e to the y. When we write the expression e to the x being a real number could either be negative, 0, or positive. The easiest situation would be x equals to 0. When we plug x equals to 0 into the definition, the entire expression in the limit equals to 1, and the limit of 1 is just 1. This means that for any real number y, e to the x plus y is simply e to the y, and 1 is equal to e to the x. Since each of the x's and the y's can be negative, 0, or positive, we have shown that this equation holds when x is 0 and y is any real number. We can likewise show that this is true whenever y is equal to 0. This is because e to the x plus y equals to e to the y plus x. And we've already proven the result when the first guy is 0. But since multiplication can be swapped, we get e to the x times e to the y. This leaves us with 4 really challenging cases. But to make our lives easy, we're going to start with the most user-friendly case when both x and y are positive. So we now claim that e to the x plus y equals e to the x, e to the y whenever x and y are both positive. Since there are a ton of inequality symbols, we'll need trick number 2, two-way inequality. To show that e to the x plus y equals e to the x, e to the y, a useful strategy is to prove that the left side is not more than the right side, and then the left side is not less than the right side. So let's first prove that the left side is not more than the right side. But this means that we have one limit being smaller than or equals to a product of limits. But since the right hand side is a product of limits, we can use this trick that the product of limits is the limit of the products. This means that we need to show that the limit on the left is not more than the limit on the right. Now, comparing the expressions inside of the limit, the two expressions look about the same except this extra xy over n squared. But x and y are both positive, meaning that xy over n squared has to be positive, which tells us that everything inside the bracket on the right is greater than everything inside the bracket on the left. When we raise both sides to the nth power, the inequality sign does not change, and we can weaken the inequality so that we can use the relative nice behavior of limits. When taking limits, the inequality sign remains the same. But since this inequality is legitimate, the inequality we are trying to show is legitimate as well, which means we have proven the first result we wanted to prove. And one half of the argument is completed. Now we need to tackle the other half. One of the most brilliant mathematicians, Terence Tao, calls this next trick an epsilon of room. We just need to fix a small positive error term and show that the left side is not more than the right side plus this error term. The idea being that as this error term goes to 0, the left side will be not more than the right side. Now the goal is to prove this modified error-inclusive formula. Let's first open up the definition of the left-hand expression and focus on the term inside the brackets. Now if somehow we manage to get rid of the xy over n squared, we're going to get the expression for e to the x plus y. But that's ridiculous. How can we just get rid of the xy over n squared without any reason? And yet, the xy over n squared term does seem really sus. We can rewrite this as 1 over n times xy over n, and if n is large enough, xy over n will get really small, in fact smaller than epsilon. This allows us to upper bound the expression by 1 plus x plus y plus epsilon all over n. Raising both sides to the nth power doesn't change anything yet again, and now we can jack n up all the way to positive infinity. On the left side, we're getting the limit of the expression, which is simply e to the x, e to the y. On the right side, taking n to positive infinity, we're going to get the limit of this expression, e to the x plus y plus epsilon. But hold up, I thought we wanted the plus epsilon to be outside of the exponential. What's that doing inside the exponential? Whatever it is doing there, something interesting happens. We can bracket the x plus y, and we've seen just now that the exponential of the sum is not more than the product of the exponentials. And yes, there isn't a plus epsilon as we had initially hoped. However, if we let epsilon go towards 0, if we can show that e to the epsilon goes to 1, we're still going to get the same result. But how do we know this for sure? This is where we'll need to reverse engineer. We now claim that e to the epsilon approaches 1. And strictly speaking, we can claim yet another result, but the proof is rather similar, and if you are interested, you can check it out in the description box below. Let's first write down the definition of e to the epsilon and focus on the term inside the limit. On the one hand, epsilon is positive and n is positive, so this entire expression will be strictly bigger than 1. On the other hand, we can expand the binomial using the binomial theorem. The binomial theorem tells us that we can expand the binomial 1 plus t to the n in the following manner. So we can plug in t equals to epsilon over n to obtain this binomial expansion. We can expand the binomial coefficient using the binomial coefficient formula, and we're going to rearrange the terms in a rather clever way. The reason for writing it this way is to observe that every fraction here is not more than 1, which means this entire expression as a whole is not more than epsilon to the k. This allows us to upper bound the right hand side by 1 plus epsilon squared all the way to epsilon to the n. But this expression is nothing more than a geometric series. The geometric series formula tells us that the sum of the first n plus 1 terms is given by the first term times 1 minus r to the n plus 1 divided by 1 minus r. In our setup, the first term is 1 and the common ratio is epsilon, and we can upper bound it by the geometric series formula. Since epsilon is meant to represent a small positive error, we'll let epsilon be smaller than 1. Since epsilon is positive and n is positive, the numerator will be upper bounded by 1. And since epsilon is smaller than 1, the denominator remains positive, and we can keep all of that as per normal. We can now summarize our findings with this two-sided inequality. Since the left side and the right side don't have any n's, we can take the limit as n goes to infinity in the middle, and this expression is nothing more than e to the epsilon. And to finally find the limit as epsilon goes to 0, we shall use the squeeze theorem. The squeeze theorem tells us that if the left and the right side approaches the same limit, so does the middle. And this is the limit we wanted to prove. Previously, we have shown that e to the x, e to the y is bounded above by e to the x plus y times e to the epsilon. But since now we know that e to the epsilon genuinely approaches 1, the left side is bounded above by the right side, and the right side simplifies to e to the x plus y. We have also previously shown that e to the x plus y is bounded above by e to the x e to the y. So we have shown that the left side is bounded above and bounded below by the right side. The only way for this to be possible is if the left side is equal to the right side. But this only proves the case for when x and y are positive. It turns out that this first case is more than enough to derive the others. But the details are a bit technical and you can check them out in the description box below. Once we have shown that this formula holds for all the different possible cases, we can now collect some freebies. This trick isn't used to prove anything for this formula, but using this formula we can derive many useful results. Firstly, we can let y equals to negative x, and this helps us get e to the x plus negative x equals e to the x e to the negative x. The left side is just e to the 0, and e to the 0 is just 1, which means we can divide out the e to the x to get e to the negative x equals the reciprocal. For positive x, when we plug it into the definition, e to the x must be positive, which means that e to the negative x is 1 over a positive number, which makes that positive as well. This means that the exponential must always be positive. Secondly, we actually derived a really useful bound on e to the epsilon. If instead of summing all the terms on the right side, we just summed from epsilon squared to epsilon to the n, we can upper bound this expression by 1 plus epsilon squared over 1 minus epsilon. This gives us a two-sided bound on e to the epsilon, which can be used to derive the limit of e to the epsilon minus 1 over epsilon. Why is this fact useful, you might ask? Because we can now calculate the derivative of the exponential, defined as the limit of the difference quotient of the exponential. Using the key exponential identity, we can split up the e to the x plus epsilon. Since e to the x has no epsilons, we can factor that out, and we have derived the limit to equal 1. These two facts then give us the property that the derivative of the exponential equals to itself. Using this, we can define that the logarithm is the inverse of the exponential. And combining the exponential and the logarithm, we can obtain the general exponential expression, which we can show satisfies the exponential property as well. For those who are interested in the proof, I've left the details in the description below. This exponential identity is so important in all of mathematics. And all it took is a bunch of tricks that we've picked up along the way to prove this result. To practice using these techniques to solve more high school problems, click on the video on the screen here.